Next, we're going to take a look at this idea of a density curve. We talked about modeling distribution. We've talked about relative standing. Okay? How do I describe a location? A density curve is very commonly used for describing distributions. Relative standing. Where am I relative to everybody else that I'm looking at? A density curve has two qualities. It always lives above the horizontal or x-axis, and it has an area of exactly 1. If it doesn't meet both of these, it's not a density curve. Anything in the world that has these two qualities is a density curve. So this could be a density curve, assuming that the area underneath it is 1. Anything at all that I want to be a density curve is a density curve as long as it lies entirely above the x-axis and has an area of 1. Density curve, as long as this area underneath it is 1, it doesn't matter what the shape is. However, we're going to spend the majority of our time on density curves that look like this. We'll get into this guy soon. My drawing kind of sucks, but should never actually touch the x-axis. It lies entirely above the x-axis and has an area of 1. You will commonly see density curves. They'll ask you questions about density curves like this, a straight line. And then we'll know that from here to here, this is 0 to 2. And they'll tell us, oh, that this height here is 0.5. However, we will not spend a whole lot of time using density curves like this. So density curve, where we talked before about skewness, left skewed density curve. Yep. Above the x-axis, the area underneath it's 1. Right skewed density curve. Yep. The curve's above the x-axis, has an area of 1. This doesn't come up very often, but this could also be a density curve. The double peaked, symmetrical density curve. Doesn't matter, guys, as long as the entire curve lies above the x-axis and the area underneath the curve is 1. Now, we talked before in chapter 1 about location of the mean and median. The sentence that we need to remember is that the mean and median both describe centers, but the mean is always on the skewed side of the median. So if you look at these first 3 up here, they're all right skewed. Okay? How do I locate the mean visually on a density curve? The mean is the balance point. If you could put your finger underneath that density curve and you had to balance it on your finger, where would your finger go? So you can see on the first one here, the fulcrum or the balance point is too far to the right. The curve would tip over to the left. If we went here, it's too far to the left, the curve would tip to the right. So the balance point, where would that point be? And you can see that here. The mean is the balance point. The median is the equal area point. The median is the point on the density curve that has equal area on both sides. So based off of these two definitions, any symmetrical density curve that we work with, the mean and median will always be in the same location directly underneath the peak. As you can see on this one to the right here, since it is right skewed, the mean must be to the right of the median. Okay? The mean is always on the skewed side of the median. They like to give us questions like this one down bottom on the right here about, can you identify the mean and median? Well, it's much easier to start by identifying the median. The median is the point where there is equal area on both sides of the graph. So maybe I think the median is C here. Well, no, this area to the right is much smaller than the area to the left. So C is not the median. Maybe the median is B. If that's the median, does it look like the same amount of area to the left and to the right? It does. So let's say that the median of this, or the equal area point, is at B. Then based off of the skewness of the curve, you should be able to tell me where the mean is. Remember, the mean is always on the skewed side of the median. So if B is the median and this is left skewed, then the mean must be A. So the mean, again, is the balance point. The median is the equal area point. When trying to identify them visually, usually easier to start with the median and then based off of the shape of the graph, determine where the mean is. Let's take a look at some normal curves. Okay, these are density curves, but a normal density curve is always symmetrical and it is always bell-shaped. Okay? The mean is always, and the median both are always directly underneath the peak. So a normal curve, we'll define normal more here in a moment. Okay? A normal curve. Notice that all of these are perfectly bell-shaped curves, perfectly symmetrical. Now, what this is going to show us is how do we identify by eye where a standard deviation is. It's going to be very important for us. In normal curves, we're going to describe these curves two ways. It's normal, big N. We need a mean and a standard deviation. The mean and standard deviation are all we need to describe the entire curve if the curve is normal. Again, normal curves are symmetrical, bell-shaped. These are density curves, so we know the area underneath the curve is 1. Where does one standard deviation lie? Well, the mean is always directly underneath the peak. And if you look at the bell shape of this curve, it goes from concave up to concave down. If you can find the point where the curvature changes or the inflection point, where it changes from concave up to concave down, that will always be one standard deviation away from the mean. So if we look at this curve here, it looks like the curvature starts to change right around here. So we drop a line straight down. This is the mean plus a standard deviation. Now we just copy this distance. There would be the mean plus 2 standard deviations. And we copy that horizontal distance again to find the mean plus 3 standard deviations. And we would do the same on the left. So if I look at this squattier normal curve, I can see the distance from the mean to one standard deviation. Again, it's the point of where the curvature changes, or what we call the inflection point. That's very important for us. They'll often ask us to draw this curve and identify where the standard deviations would lie. Well, where do these normal curves come from? What are they modeling? Well, if we took a data set, such as you can see at the top up here, if we took a data set, a histogram like this, and tried to fit a curve to it, which is what's been done with this red curve here, you'll notice that there's approximately the same amount of area of green outside the curve as there is white inside the curve. So if I could chop off all of these green parts out here, all the way around this entire curve, and place them inside the curve, it would pretty much fill in all of the white areas. So that's really all we're trying to do with a density curve. We get a set of data, and instead of finding a percentile or making a box plot or a stem plot or something like that, we're making a histogram and we're fitting a normal curve to this histogram. Well, probably the question is, what is normal? And I have not done a good job of explaining what a normal curve is. Okay, so normal has a mean underneath the peak, and it behaves the same way all the time. It's bell-shaped, it's symmetrical, and it's a density curve. So again, normal, bell-shaped, symmetrical, density curve. All of these are examples of normal curves. Now, these normal curves behave the same way always. Any data that's normal, we're going to be very happy if the data is normal, because we know exactly what's going to happen. It always has the exact same properties. Okay. One of these rules or properties for a normal curve is what's known as the 68, 95, 99.7 rule. And what it says is 68% of all the data lies within one standard deviation of the mean. So if we say that the mean is 0 and the standard deviation is 1 for this example, oh, I have a normal distribution and I describe it with 0, 1. This is always mu, sigma, always, mu, sigma. So we always describe a normal distribution with mean and standard deviation. So in this example, the mean is 0 and the standard deviation is 1. How did they know to put the 1 right here? Oh, they found the inflection point where the curvature started to change from concave up to concave down. That point was right about there, so they just dropped a vertical line there. So within one standard deviation, what does that mean? That means the mean plus and minus one standard deviation. 68% approximately of all data in any normal distribution in the world will fall in that range. So there's 68% of all the data falls within one standard deviation. 95% of all the data falls within 2 standard deviations, and 99.7 falls within 3 standard deviations. These are approximations. So if we're trying to answer questions where the data or the question falls directly on a standard deviation, this rule may be helpful. Otherwise, we will see very soon here that we can just make calculations. So the 68, 95, 99.7 rule is just a convenience rule. It also gives us an idea of how these curves behave. Every normal curve in the world behaves this way. Now, the standard normal distribution. Remember, every one of these density curves is made from bell-shaped, symmetrical density curve. Again, a density curve has an area of 1 and lies entirely above the x-axis. So as you can see on this pretty pink density curve right here, the mean is always directly underneath the peak. And then the point of curvature falls right here, or I'm sorry, the inflection point or where the curvature changes is roughly right underneath this point right here. So that's how I knew that was the mean plus a standard deviation. And then I just copy this distance, the mean plus 2, the mean plus 3, the mean minus 1, minus 2, minus 3. That's how you're going to set up every single normal curve that we do. We're going to use these normal curves so often that you'll probably get a tattoo of it on your forearm or the back of your hand. This is going to be your favorite picture. You'll put a poster above your bed at night so you can stare at it. We're going to draw hundreds, if not thousands of these throughout the course of this year. So get used to this. Now, why do we have the 0, 1, 2, 3, 0, 1, 2, 3, negative 1, negative 2, negative 3? Because this is a special normal distribution, which is called the standard normal distribution. When we standardize a value, we put it on a scale so we can compare apples to oranges, so to speak. How can I compare a 5-year-old's reading level to a 18-year-old's reading level? Well, if I standardize their scores, and you guys are probably very used to standardized scores, AP tests are standardized, SAT scores are standardized, heights of Americans, that's a standard distribution as well. Lots of data sets in the world are standardized. A standard normal distribution is the one that we spoke about a minute ago. Remember, the big N stands for, normal distribution. How do I describe a normal distribution? With the mean and the standard deviation. So normal with a mean of 0 and a standard deviation of 1. So anytime we standardize a value, we are going to convert or change the data so that it fits on this normal curve with a mean of 0 and a standard deviation of 1. Super, super helpful for us. Because what we're really going to be trying to do to find out our percentile or our relative standing is finding the area under one of these curves.